Somewhere beyond Neptune, past the last familiar landmark of our solar system, something enormous is pulling on the darkness. We cannot see it, we cannot photograph it, but we can feel it. For nearly a decade, astronomers have watched distant icy bodies behave as though an invisible hand is guiding their orbits, clustering them into patterns that should not exist by chance. The probability of coincidence is less than 1 in 10,000. So scientists went looking. They dug through decades of old infrared data, hoping to catch the faint thermal glow of a hidden world. And in 2025, a team announced they may have found something. A source in 2 separate sky surveys, separated by 23 years, showing exactly the kind of slow movement you would expect from a massive planet crawling through the outer darkness. Headlines erupted, but almost immediately the excitement unraveled. The object was too far away. It did not match the models, and when they searched with other telescopes, it was gone. Something is out there, but every time we reach for it, it slips through our fingers. Imagine you were an astronomer, not the kind who appears on television pointing at pretty nebulae, the kind who sits alone in a windowless office at 2 a.m, scrolling through spreadsheets of coordinates, cross-referencing faint blips in datasets that were recorded before you were born. You are not searching for a star. Stars are easy. They burn. They scream their presence across the electromagnetic spectrum with the confidence of a bonfire in an empty field. You are not searching for an asteroid. Asteroids reflect sunlight, and if they are close enough, they leave trails on photographic plates like tiny brushstrokes of light. No, you are searching for something far more elusive. You are searching for a planet that, if it exists, is so far from the sun that the light reaching it is less than 100,000th as strong as what falls on the Earth. A planet so cold that its surface temperature hovers somewhere around minus 220 degrees Celsius. A planet so faint that it is effectively invisible to almost every optical telescope ever built. You have no photograph. You have no confirmed position. You have no spectrum, no light curve, no transit signal. All you have is a gravitational whisper. A set of orbital anomalies in the frozen outer reaches of the solar system that keep pointing, year after year, simulation after simulation, at the same extraordinary conclusion. Something massive is hiding in the dark, and you have spent the better part of your career trying to find it. You have read every paper. You have run every cross-match your computing budget will allow. You have stared at false positives until your eyes burned, each one a small death of expectation. And you keep going, because the mathematics will not let you stop. And then, one afternoon, your algorithm flags a match. In April of 2025, a team of researchers led by Terry Long Fan published a study that sent a tremor through the planetary science community. The team was based across institutions in Taiwan, Japan, and Australia, and they had been doing something remarkably clever. They were not using a brand new billion-dollar telescope. They were not peering through the latest cutting-edge instruments suspended in orbit. Instead, they were digging through the archives. They were mining data from 2 infrared space telescopes that had completed their missions years or even decades earlier. The first was IRIS, the infrared astronomical satellite, launched by NASA in 1983. It was the very first telescope to perform a complete survey of the entire sky in infrared wavelengths, and during its 10-month mission, it catalogued hundreds of thousands of previously unknown sources. From newborn stars still wrapped in warm cocoons of natal dust, to distant galaxies blazing with the combined thermal output of 100 billion suns. When IRIS shut down, its data was archived and largely left alone, a frozen snapshot of the infrared sky from an era when personal computers were still a novelty. The second telescope was Akari, a Japanese infrared observatory that surveyed the sky between 2006 and 2007, producing the most sensitive far-infrared all-sky map ever created at the time. Akari pushed deeper than IRAS, detecting fainter sources with better angular resolution. These two missions were separated by roughly 23 years. And that gap, that seemingly mundane detail of timing, was the key to the entire experiment. Here is the logic, and it is beautifully simple. If Planet 9 exists at a distance of, say, 500 to 700 astronomical units from the Sun, it would be moving incredibly slowly across the sky. 1 astronomical unit is the distance between the Earth and the Sun, about 93 million miles. At 500 times that distance, even a planet in orbit around our star would barely appear to crawl against the background of fixed stars. The expected angular motion would be roughly 3 arc-minutes per year. To put that in perspective, the full moon spans about 30 arc-minutes across, so Planet 9 would shift by roughly 1/10 of the moon's diameter every single year. That is a tiny angular shift when measured over a single night or even a single year. But across 23 years, it adds up to more than an arc-minute of total displacement. That is something you can measure. If the same object appeared in the IRAS data at one position and then appeared in the Akari data at a slightly different position, shifted by exactly the amount you would expect for a distant body orbiting the Sun at that range, you would have a candidate. A real candidate. Not a theory on a chalkboard, not a line in a simulation, a detection. But the team was not hunting for reflected sunlight. This is a critical detail, and it changes everything about how the search works, and why it had any hope of succeeding at all. When you search for a distant planet in visible light, you are looking for sunlight that has traveled all the way out to the planet, bounced off its surface, and traveled all the way back to your telescope. The brightness of that reflected light drops with the 4th power of the distance from the Sun. If you double the distance from the Sun to the planet, the reflected brightness does not merely halve, it drops by a factor of 16. Triple the distance and it drops by a factor of 81. At 500 astronomical units, a planet even as large as Neptune would be so hopelessly dim in visible wavelengths that no existing ground-based optical telescope could realistically find it. The sunlight simply does not survive the round trip. But thermal emission plays by different rules. Every object in the universe with a temperature above absolute zero radiates heat in the form of infrared, light. The warmer the object, the more it radiates. Even a planet as cold as Planet 9 is predicted to be, warmed only slightly by its own residual internal heat, and the feeble trickle of distant sunlight would glow faintly in the far infrared part of the spectrum, and the brightness of that thermal glow decreases only with the 2nd power of the distance. That is a vastly gentler decline. It means that in infrared wavelengths, a distant planet is enormously easier to detect than in visible light. This is precisely why the team turned to IRAS and Akari. Both missions surveyed the entire sky in far infrared wavelengths. Exactly the part of the spectrum where a cold, distant planet would shine the brightest relative to its near total invisibility in optical bands. The idea was not new. Astronomers had discussed this thermal detection approach for years, but Fan's team executed it with a level of systematic rigor and specificity that had never been attempted before in a published search. The search was meticulous. They began by estimating the expected infrared flux of Planet 9 based on its predicted mass, distance, and effective temperature. They calculated how bright it should appear at 60 and 90 micrometers, which are the key observation wavelengths for both IRAS and Akari. They compared those predicted fluxes against the detection limits of both surveys and confirmed that, under reasonable assumptions about the planet's size and heat output, Planet 9 could theoretically appear in both datasets. It would be faint, right at the edge of detectability, but it would be there. Then they built their search algorithm and set it loose on the catalogs. The algorithm worked by looking for pairs. A source in the IRAS catalog at one position, and a source in the Akari catalog at a slightly different position. separated by an angular distance consistent with the slow orbital motion of a body at 500 to 700 astronomical units over 23 years. The sky is full of infrared sources, millions of them. Most are stars, many are galaxies. Some are knots of interstellar dust, heated by nearby stellar radiation. The overwhelming majority of these sources do not move. They are fixed points on the celestial sphere, pinned in place by their immense distances. A planet in our own solar system, however close it might be in cosmic terms, would drift slowly against that fixed backdrop. Finding that drift was the entire game. The algorithm returned 13 candidate pairs. 13 faint sources that appeared in both surveys with positional shifts consistent with a distant, slow-moving solar system object. The estimated heliocentric distances for these candidates fell between 500 and 700 astronomical units. The implied masses, derived from their infrared brightness and assumed temperatures, ranged between 7 and 17 Earth masses. Both of those ranges broadly aligned with theoretical predictions for Planet 9. The pulse was already quickening in the community. But 13 candidates is not a discovery. 13 candidates is a suspect lineup. The team needed to narrow it down. They began the painstaking process of elimination. They checked each candidate pair against known catalogued objects. Stars with established positions, background galaxies with measured redshifts, patches of galactic nebulae that emit strongly in the far infrared. This was essential because far infrared data is notoriously messy. The sky at these wavelengths is not a clean black backdrop dotted with neat pinpoints of light. It is a churning, foggy landscape of thermal emission from interstellar dust, filaments of galactic cirrus that stretch across the sky like ghostly veils, and dense clouds of molecular gas that glow with their own faint warmth. Any of these could mimic the appearance of a faint point source. Cosmic ray impacts on the detector could create spurious bright pixels that look exactly like real sources. Scanning artifacts from the motion of the satellite could imprint false detections into the data. Every one of these contaminants had to be identified and ruled out. One by one, the candidates fell. Some turned out to be coincidental alignments with unrelated background objects. Some were artifacts of the data processing pipeline. Some sat in regions so heavily contaminated by galactic emission that no reliable point source detection could be made at all. After visual inspection of the raw images, cross-referencing with external catalogs, and careful analysis of the detection statistics, 12 of the 13 candidates were eliminated, but one survived. One pair of detections, one source in the IRAS data, and one in the Akari data passed every test the team could throw at it. The source had appeared in the IRAS data from the early 1980s at one position in the constellation Eridanus. 23 years later, it appeared in the Akari data at a position shifted by an amount consistent with a body at the predicted distance, moving at the predicted speed across the sky. But the team did not stop there. They checked something even more specific. Akari had scanned the same patch of sky on multiple dates during its mission. If the source were a real, slowly moving solar system object, it should appear in scans taken close together in time, because the object would barely have shifted, but it should vanish from scans taken months later, because by then it would have drifted out of the narrow scan strip. They built a detection probability map. The candidate appeared in 3 scans taken on the 26th of June, 2006. It was absent from 2 scans taken on the 26th of December that same year. This was precisely the signature you would expect from a real object with slow but measurable motion. It showed up when it should have been there, in exactly the part of the scan where the geometry predicted it would lie, and it disappeared when it should have moved on. A background star would have been visible in all 5 scans. A detector artifact would have appeared randomly with no preference for one date over another. But this source behaved like something that was drifting through the field of view at the pace of a distant planet. It was, in the dry language of the scientific paper, a good candidate pair. For a brief, electrifying moment, the astronomical community was staring at the most promising Planet 9 candidate ever identified. A convergence of evidence that had simply never been assembled before. Right distance range, right estimated mass, right angular speed, right detection behavior across independent epochs. The team described it as a strong candidate and called for targeted follow-up observations using modern instruments. Specifically the dark energy camera on the Blanco 4-meter telescope in Chile, which they argued could potentially confirm or refute the detection in just a few hours of dedicated exposure time. The paper was published. The news spread through astronomy departments and science newsrooms like wildfire. And the word that nobody wanted to use but everybody was thinking hung in the air like static electricity before a storm. Discovery. Social media lit up. Science journalists scrambled to interview the authors. Some outlets ran headlines proclaiming that Planet 9 had been found. Others were more cautious but still breathless. For a few days, it felt like the decade-long search might actually be over. But this is the search for Planet 9. And in this particular search for Planet 9, hope has a very short shelf life. The first crack appeared almost immediately. When Michael Brown, one of the two Caltech astronomers who originally proposed the Planet 9 hypothesis in 2016, was asked about the candidate, his response was careful but pointed. Brown noted that the object, if real, was almost certainly too far out. His latest dynamical models, refined over nearly a decade of painstaking simulations with his colleague Konstantin Batygin, placed Planet 9 at a semi-major axis of roughly 290 astronomical units, with an updated mass estimate of about 4.5 Earth masses. The candidate from the IRAS-Akari search was sitting at 500 to 700 astronomical units, with an implied mass of 7 to 17 Earth masses. Those numbers did not match, not even close. The candidate was in the wrong neighborhood and the wrong weight class. If this object were real, it might be interesting. It might even be extraordinary. But it was probably not the Planet 9 that a decade of dynamical modeling had predicted. The second problem was more fundamental, and it could not be argued away with better instruments or deeper exposures. 2 data points do not make an orbit. Period. In astrometry, the science of precisely measuring the positions of celestial objects against the sky, you need many observations spread across a significant span of time to determine a reliable orbital solution. 2 positions separated by 23 years give you a rough direction of travel and a rough speed, but they tell you almost nothing about the shape of the orbit, its eccentricity, its inclination relative to the plane of the solar system, or where the object will be at any given point in the future. A straight line drawn through 2 points on the sky could correspond to an effectively infinite number of different elliptical orbits. To actually confirm that this object is gravitationally bound to the Sun, tracing out a closed Keplerian path, astronomers would need at minimum 9 independent positional measurements spread over a meaningful observational arc. The candidate had exactly 2. The third issue was what astronomers sometimes call the ghost problem. The team attempted to recover their candidate in data from WISE, the Wide Field Infrared Survey Explorer, another infrared space telescope that mapped the sky between 2009 and 2011. If the candidate were a real, slowly moving object, it should have been present in the WISE data at a position intermediate between its IRAS and Akari locations. But the team did not find it. The candidate was absent. Now, there are possible explanations for this absence. WISE observed at shorter infrared wavelengths than IRAS and Akari, and its sensitivity at the longer wavelengths where a cold, distant planet would emit most of its thermal radiation was comparatively limited. It is conceivable that the object was simply below the WISE detection threshold. But a non-detection is still a non-detection, and at the moment you are trying to build a case for the most significant planetary discovery in a century. Every missing piece of corroborating evidence weighs heavily. And then there was the fundamental challenge of noise. Far infrared astronomy at the sensitivity limits of these vintage space telescopes is an exercise in reading faint pencil marks on a dirty window during a rainstorm. The sources being identified are among the faintest entries in the entire catalogue. They sit right at the boundary of what the instruments could reliably measure, the twilight zone where real astrophysical signals and random detector fluctuations become nearly indistinguishable. At these margins, the line between a genuine astrophysical detection and a statistical fluctuation in the detector noise becomes agonizingly thin. A slight overestimate of the flux in one survey and a slight overestimate in another could conspire to create a phantom pair that looks, to the algorithm, indistinguishable from a slowly moving object. The team acknowledged this openly. They noted that the measured flux of the Akari source might be unreliable, and that follow-up observations were not merely desirable, but essential. This is the brutal reality of searching for Planet 9 in archival infrared data. It's not like discovering a new exoplanet by watching the regular clockwork dimming of a star as a world crosses in front of it. There is no repeating signal. There is no clean transit light curve to fit with mathematical models. There is just the faintest whisper of warmth at the bleeding edge of instrumental capability, buried in a sky saturated with thermal noise, viewed through data that is decades old and was never designed for this purpose. Every candidate that emerges from this process must run a gauntlet of verification so brutal that, to date, none has survived intact. Just 2 months later, in June of 2025, a related but independent study deepened the pattern. Another team, also working with Akari data, used a different search strategy. Instead of comparing IRAS and Akari across 23 years, they looked for sources that appeared in Akari scans taken hours apart, consistent with a stationary or very slowly moving object, but that vanished from scans taken months later, consistent with something that had drifted out of the field. They focused on a promising patch of sky between 30 and 50 degrees right ascension, a zone flagged by dynamical models as one of the most likely regions for Planet 9. After meticulously removing false positives caused by cosmic rays, background galactic dust, and instrumental artifacts, they identified 2 additional candidates whose observed positions and brightness levels fell within the predicted range for a Planet 9 type object. The study was published in the publications of the Astronomical Society of Australia and was received with cautious interest. 2 more tantalizing blips. 2 more signals that matched some predictions but had not yet been independently confirmed by any follow-up observation. 2 more faint smudges on the cosmic windshield that could be a hidden world, or could be the universe playing tricks on instruments that were never quite powerful enough to settle the question. And this is the maddening rhythm that defines this entire field. Signals emerge from the static. They excite researchers. They match some theoretical predictions while contradicting others. They fail to reappear when someone turns a different telescope to the same patch of sky. And the mystery does not shrink, it deepens. Because the gravitational evidence that something is lurking out there does not weaken when a candidate fails verification. The orbits of the most distant known objects in the solar system remain stubbornly, inexplicably clustered. The dynamical models keep demanding an unseen perturber. The mathematics keeps insisting that we are missing something massive. That tension, the yawning gap between what gravity tells us should exist and what our telescopes can actually reveal, is where the real story of Planet 9 lives. This is not a simple tale of discovery or failure. It is something far more unsettling. It is the story of an entire scientific community being haunted by an object that leaves fingerprints everywhere but refuses to show its face. The evidence says something is shaping the darkness beyond Neptune, but every time we think we have caught a glimpse of it, the image dissolves, the data contradicts itself, and we are left standing at the very edge of the known solar system. staring into an abyss of cold and silence, certain that something is staring back, but completely, maddeningly unable to prove it. The candidates do not add up. Not yet. And perhaps that is the most important phrase in this entire story. Not yet. Because the gravitational anomaly that spawned these searches, the strange orchestration of distant orbits that first made astronomers suspect something massive was out there, has not been explained away. It has not been debunked. If anything, the evidence has grown stronger over the past decade, even as every attempt to directly image the culprit has come up empty. To understand why so many brilliant scientists remain convinced that something is hiding beyond Neptune, even in the face of repeated disappointment, we need to look at the foundation upon which this entire hunt was built. We need to look at the icy bodies themselves, the most isolated objects in our solar system, and understand why they move as though they are being herded by a shepherd that no one has ever seen. To understand why the search for Planet 9 refuses to die, why brilliant scientists keep pouring years of their lives into chasing a world that no telescope has ever photographed, you have to forget about the candidates for a moment. Forget the faint infrared blips. Forget the archival data mining and the disputed detections. Instead, you have to go to the place where this story truly begins. Not a laboratory, not an observatory dome, a place far stranger and far more desolate than either. You have to travel to the outermost frontier of our solar system, past the orbit of Neptune, past the familiar ice dwarfs of the Kuiper Belt, out, into a region so remote that the sun is no longer a disk in the sky, but merely the brightest star, a cold pinprick of light barely distinguishable from the surrounding constellations. Out here, the temperature never rises above minus 230 degrees Celsius. Sunlight is so feeble that noon looks like deep twilight. And the objects that call this frozen wasteland home are among the loneliest bodies in the known universe. They are called extreme trans-Neptunian objects, or ETNOs. They are chunks of ice and rock, most of them no larger than a small country, orbiting the sun on vast, elongated elliptical paths that take thousands or even tens of thousands of years to complete a single revolution. They are so far away and so intrinsically faint that discovering even a single one of them requires long exposures on the largest telescopes in the world, often spread across multiple nights of precious observing time. As of today, we know of roughly 50 or 60 of these objects, depending on exactly how you draw the orbital boundary. That is not a lot. To put it in perspective, we have catalogued millions of asteroids in the inner solar system. Out here, beyond the gravitational reach of Neptune, the census is painfully thin. But what these few dozen objects lack in number, they make up for in strangeness, because they are not behaving the way they should. In a normal solar system, one without hidden planets or ancient gravitational disturbances, you would expect the orbits of these distant objects to be randomly oriented. Think of it like dropping a handful of sticks on the ground. Each stick lands pointing in a different direction. There is no pattern, no alignment, no preferred direction. The sticks do not care about each other, and they certainly do not conspire to point the same way. They simply fell where they fell, governed by nothing more than the random angle at which each one left your hand. The orbits of ETNOs should look the same way when viewed from above. Each orbit is an elongated ellipse, and the long axis of each ellipse should point in a random direction. The tilt of each orbit relative to the plane of the planets should vary randomly. There should be no clustering, no coordination, no conspiracy. But that is not what astronomers found. The story begins in 2014, when astronomers Chad Trujillo and Scott Shepard noticed something peculiar about a small group of the most distant known objects in the solar system. These were bodies with orbits so large that their closest approach to the Sun was still far beyond Neptune. They were gravitationally detached from the known planets. Nothing in the inner solar system could be tugging on them, nudging them, or reshaping their paths. They were, for all practical purposes, on their own. And yet, their orbits were aligned. The long axes of their elliptical paths were pointing in roughly the same direction in space. Their orbital planes were tilted at similar angles. It was as if someone had taken those randomly scattered sticks and carefully arranged them into a neat fan, all pointing the same way. Trujillo and Shepard flagged this as unusual and suggested that an unseen planet might be responsible. But at the time, the sample was tiny, only a handful of objects. It was possible, even likely some argued, that this was simply a statistical fluke. Find a few more objects, and the pattern would probably dissolve into randomness. That is what usually happens in science when you're working with small numbers. Patterns appear and then vanish as the data grows. Most astronomers noted the observation, filed it away, and moved on. But two people did not move on. In 2016, Konstantin Batygin and Michael Brown at the California Institute of Technology took the clustering seriously and decided to model it. They started with the 6 most extreme objects known at the time, those with semi-major axes greater than 250 astronomical units and perihelia beyond 30 astronomical units, meaning they never came close enough to Neptune for the ice giant to influence their orbits. They examined the alignment of these 6 orbits and calculated the probability that such clustering could occur by random chance alone. The number they arrived at was 0.007%. That is roughly 1 chance in 14,000. In statistical terms, it meant the clustering was almost certainly not a coincidence. Something was causing it. Batygin and Brown then asked the obvious follow-up question. What kind of object could produce this pattern? They ran extensive numerical simulations of the outer solar system, testing different configurations of a hypothetical massive body. They varied its mass, its orbital distance, its eccentricity, and its inclination. They watched how each configuration affected the orbits of the small bodies over billions of years of simulated time. And they found a solution. A single planet, roughly 10 times the mass of the Earth at the time of their initial estimate, orbiting the Sun on a distant, elongated path with a semi-major axis of roughly 700 astronomical units. The key feature of this planet's orbit was that it was anti-aligned with the clustered ETNOs. Its closest approach to the Sun was on the opposite side of the sky from the closest approaches of the small bodies it was herding. This anti-alignment created a gravitational resonance, a dynamic equilibrium that kept the ETNOs locked in their clustered configuration over the age of the solar system. This was not a vague hand-waving explanation. It was a specific, testable, mathematically rigorous prediction. The simulation showed that the hypothetical planet did not merely explain the clustering of the 6 known extreme objects. It also predicted the existence of a population of objects on highly inclined orbits, tilted nearly perpendicular to the plane of the planets. At the time, Batygin and Brown published their paper. 5 such objects were already known. Nobody had been able to explain why they existed. Planet 9 explained them naturally, as a dynamical consequence of the same gravitational influence that produced the clustering. It was as if the model had reached out and solved a second puzzle that nobody had even asked it to solve. The scientific community took notice. The paper was published in the Astronomical Journal in January of 2016, and it detonated like a slow-burning bomb across planetary science. Within months, research groups around the world began searching for the predicted planet and testing the hypothesis against new data. The reaction was a mixture of excitement and skepticism, which is exactly what you want in science. Some astronomers immediately began planning observational campaigns with the largest telescopes on Earth. Others started looking for weaknesses in the argument. Both responses were valuable, both were necessary. Over the following years, the evidence did not weaken, it grew. As more ETNOs were discovered by ongoing surveys, the clustering persisted. New objects kept falling into the same aligned pattern that Batygin and Brown had identified. The sample was no longer 6 objects. It grew to a dozen, then beyond. Each new discovery was a chance for the pattern to break, for the alignment to dissolve into the noise, but it did not break. Brown and Batygin developed methods to quantify the observational biases in the ETNO sample, attempting to determine whether the clustering could be an artifact of where and when telescopes happened to be pointing. In 2019, they published an analysis concluding that even after accounting for these biases, the probability of the clustering being random was approximately 0.2%, one chance in 500. The pattern was stubborn. It refused to go away. But the gravitational case for Planet 9 was not built on clustering alone. That was the headline, the attention grabber, the feature that made it into popular science articles and YouTube thumbnails. Beneath the headline, there were other lines of evidence, less flashy but equally compelling. And taken together, they formed something much stronger than any single observation. Consider the strange case of objects on highly inclined orbits. In the plane of the solar system, the 8 known planets all orbit within a few degrees of a common flat disk, the ecliptic. This is a relic of the solar system's formation from a spinning disk of gas and dust. Everything that condensed out of that disk inherited its rotation, which is why the planets all orbit in roughly the same plane. But out beyond Neptune, there are objects that orbit at extreme inclinations, some tilted 60, 70, even 90 degrees relative to the ecliptic. Some of them orbit in a retrograde direction, meaning they go around the sun backwards compared to everything else. These objects are deeply weird. In a solar system shaped only by the 4 known giant planets, producing such extreme inclinations is extraordinarily difficult. The gravitational kicks required to tilt an orbit that dramatically are simply not available from Jupiter, Saturn, Uranus, or Neptune at those distances. But Batygin and Brown's simulations showed that Planet 9 could do it. The same gravitational resonance that clusters the ETNOs also acts as a long-term torque, slowly rotating the orbital planes of certain objects until they end up on these wildly tilted paths. The model predicted the existence and approximate distribution of high-inclination objects before many of them had even been discovered. When the discoveries came, they matched. There was also the peculiar tilt of the Sun itself. The spin axis of the Sun is offset by about 6 degrees relative to the orbital plane of the planets. This is a small but persistent misalignment that has puzzled astronomers for decades. In most models of solar system formation, the Sun's equator and the planetary orbits should be nearly perfectly aligned. The 6-degree tilt was a loose thread in the tapestry. In 2016, shortly after the Planet 9 hypothesis was published, Elizabeth Bailey, a graduate student working with Batygin and Brown, showed that a distant massive planet on an inclined orbit could, over the 4.5 billion year history of the solar system, exert a slow, gravitational torque on the entire plane of the inner planets, gradually tilting it relative to the Sun's spin axis. Planet 9 could explain the tilt. It was another puzzle solved for free, another prediction that fell out of the model without being specifically designed into it. Then, in 2024, the case took what many considered its most significant leap forward. Batygin, Brown, and their collaborators published a new analysis focused on a specific population of objects that had previously been overlooked in the Planet 9 debate. These were low-inclination, trans-Neptunian objects that cross Neptune's orbit. They are not the extreme, far-flung ETNOs that originally inspired the hypothesis. They are closer, more accessible objects whose orbits bring them into the gravitational neighborhood of the known giant planets. The team ran detailed dynamical simulations comparing 2 scenarios. In one scenario, the outer solar system contained only the 4 known giant planets. In the other, it contained the 4 giants plus Planet 9. They then compared the predicted distributions of these Neptune-crossing objects against the observed data. The result was striking. The scenario without Planet 9 failed to reproduce the observed distribution of these objects. It could not explain their orbital properties. But the scenario with Planet 9 matched the data with remarkable precision. The Planet 9 free model was rejected at a confidence level of approximately 5 sigma. In particle physics, 5 sigma is the gold standard for a discovery. It is the threshold that was used to confirm the existence of the Higgs boson. Now, the standards in planetary science are not identical to those in particle physics, and this result should be interpreted with appropriate caution. But the statistical strength of the finding was extraordinary. It was, by the metrics of the field, the single strongest piece of dynamical evidence yet produced in favor of the hypothesis. By 2025, the theoretical picture had been refined further still. A study by Amir Siraj, Christopher Chiber, and Scott Tremaine used an expanded sample of 51 extreme trans-Neptunian objects to run 300 independent simulations of the outer solar system. They were not simply testing whether Planet 9 could exist. They were trying to pin down exactly what it would look like. Their results narrowed the predicted mass to 4.4 plus or minus 1.1 Earth masses, significantly smaller than the original estimate of 10 Earth masses. The predicted semi-major axis came down to roughly 290 astronomical units, with an eccentricity of about 0.29 and an inclination of approximately 6 degrees. This was a leaner, closer, more refined Planet 9 than the one originally proposed. It was also, importantly, a Planet 9 that would be within the survey capabilities of the Vera C. Rubin Observatory, the powerful new telescope in Chile that began its operations in 2025. So this is the foundation upon which the entire hunt rests. It is not a single observation. It is not a single clever argument. It is an interlocking web of gravitational evidence, each strand reinforcing the others. The clustering of extreme trans-Neptunian objects, the existence of high inclination and retrograde orbits that no known planet can produce, the anomalous tilt of the sun's spin axis, the orbital distribution of Neptune crossing, objects that statistically demands an additional massive body. Each of these lines of evidence, taken alone, might be dismissed as a curiosity or explained away by some alternative mechanism. But together, they form a pattern so coherent and so persistent that ignoring it requires either extraordinary coincidence or a willingness to reject the mathematics. And here is the part that keeps astronomers awake at night. Every one of these gravitational signatures is indirect. They are shadows on the wall. They are footprints in the snow. They tell you that something walked through this landscape. Something heavy. Something real. But they do not show you the creature itself. You can measure the depth of the footprint. You can calculate the weight of the animal. You can predict the direction it was heading. But when you look up from the tracks and scan the horizon, the landscape is empty. The creature is gone. Or is still there, hiding in plain sight against a background so vast and so dark that even our best instruments cannot distinguish it from the void. This is the central paradox of the Planet 9 hypothesis, and it is what makes this story so fundamentally different from any previous planetary discovery. In every prior case where gravitational anomalies pointed to a hidden world, the telescopes delivered. The prediction was followed by confirmation, sometimes within days. With Planet 9, the gravitational theory is arguably stronger than any that came before. The lines of evidence are more numerous. The statistical confidence is higher, but the confirmation refuses to come. Part of the reason is simply distance. Neptune orbits at 30 astronomical units. Planet 9, if the 2025 models are correct, orbits at roughly 290. That is nearly 10 times farther away. And because brightness falls so steeply with distance, the observational challenge is not 10 times harder. It is thousands of times harder. Planet 9 is predicted to have an apparent magnitude somewhere around 22 to 25, depending on its exact size, composition, and current position along its orbit. That places it within the reach of the largest ground-based telescopes, but only barely, and only if you know exactly where to point them. The predicted orbit traces a vast arc across the sky, covering a strip that could take years to search systematically, even with wide-field instruments. And the problem is compounded by the nature of the object itself. Planet 9 is not expected to be a gas giant like Jupiter or Neptune, blazing with reflected sunlight and surrounded by a retinue of moons. Based on the 2025 mass estimate of 4 to 5 Earth masses, it is more likely a super-Earth, a dense, rocky or icy world with a relatively small cross-section and a modest albedo. It would reflect less light per unit of surface area than a puffy gas envelope. It would be dimmer, smaller in angular size, and harder to distinguish from the countless faint background stars and galaxies that populate every square degree of the deep sky. Astronomer Renu Malhotra of the University of Arizona has pointed to another layer of the challenge. She has noted that we observe only the brightest of these distant objects, and only a tiny fraction of even those, because we catch them only when they swing closest to the sun. Our entire census of the outer solar system is based on a sliver of what is actually out there. We are looking through a keyhole and trying to map a cathedral. The patterns we see in the ETNO orbits may be real, but Malhotra cautions that with so few objects and so much observational selection at work, we should be careful about how much weight we place on the clustering. Despite all of this, the community has not given up. The gravitational evidence is too strong to ignore. The clustering is too statistically significant to dismiss. The multiple independent lines of evidence are too neatly interlocking to be coincidental. Something is shaping the architecture of the outer solar system. The mathematics demands it. The simulations confirm it. The observations are consistent with it. And every few years, the models are refined, the predicted parameters are tightened, and the search area narrows. But the planet itself remains invisible. It is the most rigorously predicted unseen object in the history of astronomy. Its mass, its distance, its orbital shape, its inclination, even its approximate position on the sky have all been estimated through the gravitational fingerprints it leaves on its neighbors. We know more about this hypothetical planet than we knew about Neptune before its discovery. And yet, Neptune was found in a single night of observing. Planet 9 has eluded every search for nearly a decade. This is what makes the 2025 candidate detections so tantalizing and so frustrating at the same time. The infrared blips in the IRAS and AKARI data were exciting precisely because they offered the possibility of bypassing the indirect evidence entirely. They offered a direct sighting, a thermal glow from the object itself. But as we have already seen, those candidates came with cracks that could not be papered over. Wrong distance, wrong mass, missing from other surveys. Too few data points for an orbit. The candidates pointed to something, but whatever they pointed to did not match the specific object that the gravitational models had spent a decade describing. And so the hunt continues. The gravitational fingerprints grow deeper and more numerous with each new ETNO discovery. The theoretical models grow sharper with each new simulation. The predicted planet grows more defined, more constrained, more real in every sense except the one that matters most. We still cannot see it. We are in an extraordinary situation, one that has almost no precedent in the history of science. We have overwhelming circumstantial evidence for the existence of a major solar system body. We have mathematical models that describe its properties with remarkable specificity. We have multiple independent reasons to believe it is there, and we have absolutely no direct observation to confirm it. This is not a failure of science. It is science operating at the extreme edge of its capabilities, reaching for an object that sits right at the boundary between what we can infer and what we can prove. The gravitational evidence says the shepherd is real. The telescopes say the shepherd is invisible. And until one of those statements yields, we are trapped in the most productive and most maddening paradox in modern planetary science. But the gravitational argument, as powerful as it is, still rests on an assumption. It assumes that the orbital patterns we observe are caused by a single massive object. It assumes that no other mechanism could produce the same signatures. And it assumes that our observations of the outer solar system, thin and biased as they are, accurately reflect the true distribution of objects out there. Each of those assumptions has been challenged, each has been defended, and the debate over whether those assumptions hold is every bit as fierce and every bit as fascinating as the search for the planet itself. Because if the assumptions are wrong, then the invisible shepherd might not be a planet at all. It might be something far stranger, or it might be nothing more than a trick of the light. If the gravitational case for Planet 9 is so strong, if the mathematics is so compelling and the evidence so neatly interlocking, then why on earth have we not found it yet? This is the question that haunts every astronomer who works on this problem. It is the question that critics love to throw at conferences, the question that journalists ask in every interview, and the question that sits like a stone in the stomach of every researcher who has spent nights at a telescope searching for a faint dot that never appears. The answer is not simple. It is not a single obstacle. It is a cascading series of compounding difficulties, each one multiplying the challenge of the last, until the total problem becomes one of the most punishing observational gauntlets in the history of astronomy. Finding Planet 9 is not like finding a needle in a haystack. It is like finding a specific grain of black sand on a dark beach at midnight, using a flashlight with a dying battery while the tide keeps shifting the sand beneath your feet. Let us start with the most basic problem: distance. Everything about the difficulty of this search traces back, in one way or another, to how far away Planet 9 is predicted to be. The 2025 models place it at a semi-major axis of roughly 290 astronomical units. To grasp what that means in human terms, consider that the Earth orbits the Sun at 1 astronomical unit, roughly 93 million miles. Neptune, the outermost known planet, orbits at 30 astronomical units. That is already almost 3 billion miles from the Sun. Planet 9, at 290 astronomical units, would be nearly 10 times farther out than Neptune. It would be roughly 27 billion miles from the Sun. Light itself, traveling at 186,000 miles per second, would take more than 40 hours just to make the one-way journey from the Sun to Planet 9. At that distance, you are no longer in the familiar neighborhood of the planets. You are in the wilderness. You are in a region of space so vast and so empty that the Sun has shrunk to a brilliant but tiny star, and the warmth it provides is essentially zero. Now, consider what distance does to brightness. We have already seen that reflected sunlight drops with the fourth power of distance, which is why the infrared approach was so attractive. But even the gentler decline of thermal emission, which falls only with the second power, does not make this problem easy. At our 290 astronomical units, the numbers are devastating. In reflected light, Planet 9 would be roughly 8,700 times fainter than a comparable object at Neptune's distance. It is like trying to read a book by the light of a candle that is not across the room, but across the entire city. Even in the infrared, the situation is barely survivable. But even in the infrared, the signal from Planet 9 is predicted to be extraordinarily faint. The expected flux at 60 to 90 micrometers, the wavelengths where a cold planet would emit most of its thermal radiation, sits right at or just above the detection limits of the best far-infrared space telescopes we have ever built. IRAS, launched in 1983, had a sensitivity limit of roughly 0.2 Janskis at 60 micrometers. Akari could reach roughly 0.21 Janskis at 65 micrometers. Planet 9's predicted brightness hovers in exactly that range, depending on assumptions about its mass, temperature, and composition. We are not looking for a bright beacon in the infrared sky. We are looking for a source so faint that it sits on the razor's edge between detectable and invisible, fluctuating above and below the noise floor depending on which set of assumptions you choose to believe. And that noise floor is not a clean, flat surface. The far infrared sky is one of the most treacherous observational environments in all of astronomy. At optical wavelengths, the sky between the stars is mostly dark. There are a few scattered sources, but the background is generally clean. In the far infrared, the situation is completely different. The entire galaxy glows. Interstellar dust, heated by the diffuse radiation field of billions of stars, emits a pervasive fog of thermal radiation that blankets the sky. This emission is strongest along the plane of the Milky Way, but it extends far above and below the galactic equator in wispy, tangled filaments called galactic cirrus. These filaments are everywhere. They are irregular, they are unpredictable, and they can easily mimic the appearance of a faint point source in a low-resolution infrared survey. A tiny knot of warm dust, a slight overdensity in a cirrus filament, a clump of molecular gas heated by a nearby star, any of these can produce a blip in the data that looks, at first glance, like a candidate planet. This is the contamination problem, and it plagued the IRAS-AKARI search from the beginning. The team had to visually inspect every candidate against maps of galactic emission, checking whether the detected source could be explained by a patch of bright dust rather than a moving solar system object. For candidates located near the galactic plane, this task was nearly impossible. The emission was too bright, too structured, and too variable to allow confident detection of a faint point source embedded within it. This is why the major portion of the sky in far infrared wavelengths has been effectively ruled out as a search zone. If Planet 9 happens to be located along a line of sight that passes through a dense region of galactic dust, it may be undetectable in archival far infrared data, regardless of how bright it actually is. The background simply drowns it out. Then there are the instrumental artifacts. Space telescopes are extraordinary machines, but they are not perfect. IRAS scanned the sky by spinning slowly while its detectors recorded the infrared radiation falling on them. This scanning motion introduced systematic patterns into the data. Certain types of electronic noise in the detectors could produce spurious signals that appeared at regular intervals along the scan direction. These artifacts were well understood and mostly removed during data processing, but at the faintest detection levels, some residual contamination inevitably remained. A faint artifact in one survey, coincidentally located near a faint artifact in another survey at the right angular separation, could mimic the signature of a slowly moving object. The probability of such a coincidence is low, but when you are searching millions of source pairs across the entire sky, low probability coincidences happen. This is one of the reasons why 13 candidate pairs were found in the IRAS-AKARI search, but only one survived the vetting process. The others were likely some combination of background contamination, artifacts, and statistical noise conspiring to look like something they were not. Cosmic rays add another layer of frustration. High-energy particles from deep space constantly bombard the detectors of any space telescope. When a cosmic ray strikes a pixel on the detector, it deposits a burst of energy that looks like a bright point source. These cosmic ray hits are usually easy to identify because they appear in only a single frame and do not repeat. But the detection algorithms used to build source catalogs are designed to be sensitive, and occasionally a cosmic ray hit can survive the cleaning process and end up listed as a real source. If that happens in both the IRAS and AKARI, catalogs at positions that are coincidentally separate by the right angular distance, you get a false candidate pair. Again, the probability is small for any given pair of pixels, but multiplied across the entire sky and across tens of thousands of faint catalog entries, these false matches accumulate. Now, let us move beyond the archival infrared searches and consider the optical surveys, because those have also come up empty, and the reasons for their failure tell us something important about the nature of the quarry. Over the past decade, some of the most powerful wide-field telescopes in the world have been pointed at the sky regions where Planet 9 is most likely to be, and they have found nothing. The Subaru telescope on Mauna Kea in Hawaii, equipped with its Hyper Supreme Cam, one of the most capable wide-field cameras in existence, conducted targeted searches of the predicted Planet 9 sky regions between 2015 and 2023. The camera covers a field of view of 1.5 degrees across, and it can detect objects as faint as magnitude 26 in long exposures. The team searched high-priority areas of the sky that dynamical models had flagged as the most probable locations for the planet. They found nothing. Their non-detection was significant. It effectively ruled out approximately 50% of the predicted locations for the nominal Battigan-Brown model, constraining the possible semi-major axes and perihelion distances that Planet 9 could have. But ruling out 50% of a vast search area still leaves 50% unsearched. And the unsearched regions tend to be the hardest ones. The patches of sky where the planet would be farthest from the sun along its orbit, at its faintest, moving at its slowest, and most easily confused with the dense fields of background stars and galaxies in those directions. The Subaru searchers did something else important though. They discovered new trans-Neptunian objects, adding to the census of the outer solar system. Each new discovery helped refine the dynamical models, tightening the predicted parameters of Planet 9, but the planet itself remained elusive. The TESS mission, the Transiting Exoplanet Survey satellite, also contributed to the search, though it was never designed for this purpose. Researchers Milena Rice and Gregory Laughlin applied a technique called shift stacking to TESS data, digitally shifting successive images by the amount a distant object would move between frames, and then stacking them together to boost the signal. This is an elegant trick. If there is a faint object moving at a specific rate across the field, the shift stacking brings its light into focus while smearing out everything else. The technique can detect objects that would be invisible in any single exposure. They applied it to TESS sectors 18 and 19, covering a portion of the sky relevant to the Planet 9 search. Their results generated no serious evidence for the planet. However, they did identify 17 new candidate outer solar system objects at distances between 80 and 200 astronomical units. These candidates required ground-based follow-up to confirm. Early attempts to recover 2 of them using the William Herschel telescope failed. The candidates could not be found at their predicted positions. They had either moved beyond the recovery search area, or they were never real objects in the first place, just statistical fluctuations in the stacked data that happened to look like slowly moving sources. This pattern of detection, followed by failed recovery, is one of the most demoralizing features of outer solar system astronomy. You find a promising signal. You calculate where the object should be at a later date. You apply for telescope time, wait weeks or months for your scheduled night, point the telescope at the predicted position, and see nothing. Either the object was not real, or your prediction of its future position was wrong because you did not have enough data to compute an accurate orbit, or the object is real but has moved to a position slightly outside your search field because the orbital uncertainties were larger than you estimated. Every one of these outcomes is plausible, and every one of them sends you back to the beginning with nothing to show for the effort except a slightly better understanding of where the object is not. Then there is the broader WISE problem. We already know the Ira-Zakari candidate could not be recovered in WISE data, but the issue extends far beyond a single candidate. The entire WISE archive has been exhaustively searched for any sign of a distant massive planet, not just at the coordinates of the 2025 candidates, but across the full sky. Nothing has been found. The non-detection constrains the maximum brightness, and therefore the size and temperature, of any large body lurking in the outer solar system. It does not rule Planet 9 out, because the planet's peak thermal emission falls at wavelengths beyond what WISE could detect. But it closes yet another door and tightens the box around what Planet 9 can be. The planet, if it exists, must be cold enough, small enough, and distant enough to have slipped beneath every infrared survey we have ever conducted. The cumulative effect of all these non-detections is psychologically devastating, but scientifically informative. Each failed search eliminates a portion of the parameter space. Each non-detection tells us where Planet 9 is not, which narrows the region where it could be. This is how astronomy often works. You do not find what you're looking for. You chip away at the darkness until the remaining unexplored region is small enough that the next generation of instruments can finish the job. It is a war of attrition, and the astronomers are winning, but slowly. This brings us to a fundamental asymmetry that defines the Planet 9 problem. It is vastly easier to hide this planet than to find it. Consider the geometry. Planet 9's predicted orbit has a period of roughly 5,000 years. That means it takes 5 millennia to complete a single lap around the Sun. At any given moment, it occupies one specific point along that vast orbital arc. We do not know which point. The dynamical models can tell us the shape of the orbit and its orientation in space, but they cannot tell us where along the orbit the planet currently sits. It could be near its closest approach to the Sun, at roughly 200 astronomical units, where it would be at its brightest and most detectable. Or it could be near its most distant point, at nearly 400 astronomical units, where it would be so faint that even the largest telescopes would struggle to see it. The difference in brightness between these two extremes is enormous, a factor of perhaps 10 or 20 in reflected light, and a factor of 4 or more in thermal emission. If Planet 9 happens to be near aphelion right now, near the far end of its orbit, it may be beyond the reach of every instrument currently in operation. And there is another subtlety that makes the search even harder. Planet 9 moves slowly, excruciatingly slowly. At 290 astronomical units, its angular motion across the sky is roughly 2 to 3 arc-minutes per year. That is about 1/10 the apparent diameter of the full moon per year. In a single night of observing, it would barely move at all. This means that in a single exposure, Planet 9 would look exactly like a star. It would be a faint, stationary point of light, indistinguishable from the billions of background stars that populate the deep sky. The only way to identify it as a solar system object is to observe the same patch of sky on multiple nights, separated by weeks or months, and look for a source that has shifted slightly against the fixed background. This technique, called blinking or digital shift detection, is well established. It is how Clyde Tombaugh discovered Pluto in 1930, but it requires knowing where to look, and it requires that the target be bright enough to appear in the individual exposures. If Planet 9 is too faint for a single exposure, you need more sophisticated techniques like the shift stacking method, which computationally tries millions of possible motion vectors to see if any of them bring a hidden signal out of the noise. This works, but it is computationally expensive, and it generates enormous numbers of false positives that must be individually vetted. The sky itself conspires against us as well. The region of the sky where Planet 9 is predicted to be is not empty. It is populated by dense star fields, particularly where the predicted orbit passes near the plane of the Milky Way. In these crowded fields, a faint, slowly moving object can be masked by the glare of brighter nearby stars, lost in the confusion of overlapping stellar profiles, or simply overwhelmed by the sheer number of sources that have to be checked. Even automated detection pipelines struggle in these regions. They flag thousands of candidates per square degree, most of which are artifacts or misidentified background objects. And the human effort required to sort through them is staggering. This is the comprehensive picture of why the search keeps failing. It is not any single factor. It is the multiplicative combination of extreme distance, feeble brightness, contaminating backgrounds, instrumental limitations, vast orbital uncertainty, glacial angular motion, and the brute statistical challenge of finding one faint moving object among billions of stationary ones. Each of these problems alone would be manageable. Combined, they create an observational fortress that has resisted every assault for nearly a decade. But the fortress may be about to fall. The Vera C. Rubin Observatory, perched atop Cerro Pachon in the Chilean Andes, achieved first light in mid-2025 and has begun what is expected to be the most comprehensive sky survey in the history of ground-based astronomy. Its primary instrument is the Legacy Survey of Space and Time, or LSST, which will photograph the entire visible southern sky every few nights for 10 years. The telescope carries the largest digital camera ever built, a 3.2 gigapixel monster that can image a field of view 3.5 degrees across in a single exposure. It is designed to detect objects as faint as magnitude 24.5 in a single 30-second visit, and significantly fainter when multiple visits are combined. Over the course of a decade, it will catalogue an estimated 10 billion objects, including millions of solar system bodies. For the Planet 9 search, Rubin represents a qualitative leap. Previous searches have been targeted. Astronomers chose specific patches of sky based on their best guess of where the planet might be, observed those patches intensely, and then moved on. Rubin does not work that way. It photographs everything, everywhere, all the time. If Planet 9 is within its detection limits and within its survey footprint, it will appear in the data, not once, but hundreds of times over the course of the survey, automatically generating the multi-epoch coverage needed to identify a slowly moving source and compute its orbit. Estimates suggest that Rubin has a greater than 60% chance of detecting Planet 9 if it exists with the properties currently predicted by the dynamical models. Those are not certainty level odds, but they are dramatically better than anything that has come before. However, even Rubin has its limits. If Planet 9 is smaller than predicted, or colder, or farther out along its orbit, or if it has a particularly dark surface that reflects very little light, it could slip below Rubin's detection threshold. The 60% figure is an average across the range of plausible parameters. For some corners of that parameter space, the detection probability drops to near zero. And Rubin only observes the southern sky. If Planet 9's current position happens to be in the northern celestial hemisphere, Rubin will not see it at all, though the Subaru telescope and other northern instruments will continue their searches. There is also the question of time. Rubin's survey will run for 10 years. The full sensitivity of the search will only be realized after multiple years of accumulated data, as the software pipelines refine their catalog of moving objects and the shift stacking algorithms have enough epochs to detect the slowest movers. The first year of data will be revealing, but it may not be sufficient. It may take 3, 5, or even the full 10 years before the survey can definitively confirm or rule out Planet 9 across the full range of predicted parameters. This is not a sprint, it is a marathon, and we are still in the early miles. But what if Rubin runs for a decade and finds nothing? What if the most powerful survey telescope ever built scans the entire southern sky hundreds of times over and comes up empty? That outcome would not necessarily kill the Planet 9 hypothesis, but it would wound it severely. It would force a reckoning. If the planet cannot be found where the models predict it should be, at the brightness the models predict it should have, then either the models are wrong, the planet does not exist, or something about its properties is radically different from what we currently assume. Each of those possibilities opens a different door, and behind some of those doors are explanations that are every bit as strange as a hidden planet. Because the truth is, even as the search for Planet 9 grinds forward with ever more powerful instruments, a parallel debate has been raging. A debate not about where the planet is, but about whether it exists at all. A growing number of astronomers have been arguing that the gravitational signatures attributed to Planet 9 might have entirely different explanations, that the clustering might be an illusion, that the orbital anomalies might be produced not by a single massive body, but by a collective effect, or a bias in our observations, or even a flaw in our understanding of gravity itself. These are not fringe objections. They are serious, peer-reviewed challenges from respected scientists who have looked at the same data and reached very different conclusions. And the evidence they have assembled deserves the same careful attention we have given to the case in favor. There is a dangerous comfort in a good theory. When a hypothesis explains multiple phenomena at once, when the simulations produce elegant curves that match the data, when the statistical significance keeps climbing year after year, it is tempting to treat the case as closed, to assume that the only remaining question is where, not whether. But science has a long and humbling history of beautiful theories that turned out to be wrong. And the Planet 9 hypothesis, for all its mathematical elegance, has attracted a formidable roster of skeptics who believe the evidence can be explained without invoking a hidden planet at all. These are not contrarians for the sake of controversy. They are careful scientists who have identified genuine vulnerabilities in the argument, and their objections deserve to be taken as seriously as the evidence they challenge. The first and most persistent objection strikes at the very foundation of the hypothesis. It attacks the clustering itself. Remember, the entire case for Planet 9 begins with the observation that the orbits of extreme trans-Neptunian objects are aligned in a way that should not happen by chance. Battigan and Brown calculated the probability of random clustering at roughly 1 in 14,000. That sounds impossibly unlikely. But there is a catch, and it is a catch that has plagued observational astronomy since the invention of the telescope. It is called observational bias. Observational bias is the distortion that creeps into your data when you can only observe part of the sky, or only observe at certain times, or only detect the brightest objects in a given direction. It is the astronomer's version of the streetlight effect. The old joke about the man searching for his keys under a lamppost. Not because he lost them there, but because that is where the light is. In the case of extreme trans-Neptunian objects, the bias is severe. These objects are extraordinarily faint. They can only be detected when they are at or near their closest approach to the sun, at perihelion, when they are as bright as they will ever get. For the rest of their orbits, which span thousands of years, they are too dim to see. This means we only ever observe them in a narrow slice of their orbital arc. We are watching runners in a marathon, but only seeing them as they pass a single checkpoint. We have no idea what the rest of the course looks like. Now compound that with the fact that telescopes do not observe the entire sky uniformly. Different surveys cover different patches of sky at different depths. Some regions have been surveyed intensively by large telescopes. Others have been barely touched. The distribution of telescope time is determined by weather, scheduling, the latitude of the observatory, the scientific priorities of the community, and 100 other practical factors that have nothing to do with where distant icy bodies happen to be. This means that the specific objects we have found, the specific ETNOs, whose orbits form the clustering pattern, are not a random sample of all ETNOs that exist. They are a biased sample, filtered through the idiosyncrasies of where and when we happen to look. Samantha Lawler, an astronomer at the University of Regina in Canada, has been one of the most vocal and rigorous critics on this point. She worked on the Outer Solar System Origin Survey, known as OSSOS, which used the Canada-France-Hawaii telescope to systematically search 8 carefully selected patches of sky between 2013 and 2017. OSSOS was specifically designed to quantify and correct for observational biases. The survey discovered more than 800 new Kuiper Belt objects, including 8 ETNOs with average distances from the Sun greater than 150 astronomical units. These are precisely the kind of objects whose clustering is supposed to be evidence for Planet 9. But in the OSSOS sample, the orbits were not clustered. They were scattered in various directions. There was no alignment. The pattern that Battigan and Brown had identified in the pre-existing sample simply did not appear in this independently gathered, bias-controlled dataset. Lawler and her colleagues argued that the Clustering seen in the earlier data could be entirely an artifact of uneven sky coverage. If you happen to discover most of your ETNOs in the same part of the sky, using the same telescopes, during the same observing seasons, then of course their orbits will appear to point in similar directions. You are not seeing a physical pattern, you are seeing the shape of your own observing strategy reflected back at you. The OSSOS results could not definitively rule out Planet 9, but they demonstrated that the clustering evidence was far more fragile than it appeared. It depended heavily on which objects you included in your sample, and how carefully you accounted for the way those objects were found. Batagian and Brown pushed back. They developed their own methods for quantifying observational bias, and published a 2019 analysis arguing that even after correction, the clustering remained statistically significant at the 0.2% level. But the debate is not settled. Lawler and others have countered that the bias corrections themselves depend on assumptions about the intrinsic population of ETNOs, assumptions that are necessarily uncertain given how few of these objects we know. Different assumptions about the total number and distribution of distant objects lead to different bias corrections, which lead to different conclusions about whether the clustering is real. The argument is circular in a way that cannot be broken without a much larger sample of discoveries, which is precisely what the Vera C. Rubin Observatory is expected to provide. Until then, the clustering remains contested. But the challenges to Planet 9 do not stop at observational bias. Even if the clustering is real, even if the orbits genuinely are aligned in a way that demands an explanation, there are scientists who argue that the explanation does not have to be a planet. One of the most intriguing alternative proposals is the idea of collective gravity, sometimes called the self-gravity hypothesis. The basic concept is straightforward. What if the outer solar system contains not one massive object, but a large number of smaller ones whose combined gravitational influence mimics the effect of a single planet? Imagine a dense ring of icy debris encircling the Sun at great distance. Each individual object in the ring is too small to have any measurable gravitational effect on its own. But if the ring is massive enough, if it contains enough material spread across a wide enough band, then its collective gravity could nudge the orbits of the ETNOs in a coherent way. The gravitational pull of the ring would not come from a single direction, as it would from a planet. It would be distributed, diffuse, and subtle. But over billions of years of gentle, persistent tugging, it could produce the same kind of orbital clustering that Batagian and Brown attributed to Planet 9. This idea is not without precedent. We know that rings of debris exist around other stars. Observations of young stellar systems frequently reveal broad disks and rings of dust and ice extending to hundreds of astronomical units. Some of these rings are thought to be maintained by the gravitational influence of unseen planets, which complicates the argument rather than settling it. But the basic principle that a distributed mass can produce coherent gravitational effects is well established in physics. The question is whether the outer solar system contains enough material to do the job. Current estimates of the total mass of the Kuiper belt and the scattered disk are well below what would be needed. But those estimates are based on the same biased observations that are at the heart of the clustering debate. If there is a vast population of small, dark, cold objects beyond the detection limits of our current surveys, we would not know about them. The absence of evidence is not evidence of absence, especially when you are searching in the hardest part of the sky to observe. Then there is the discovery that rattled the Planet 9 camp more than any statistical argument. In July of 2025, astronomers using the Subaru telescope announced the detection of a new sednoid, one of the rarest and most extreme classes of trans-Neptunian objects. The object was designated 2023 KQ14 and given the informal nickname Ammonite after the spiral-shelled fossil, because it was discovered as part of a survey called Fossil, the Formation of the Outer Solar System, an icy legacy project. Ammonite was only the fourth sednoid ever found, joining Sedna, 2012 VP113, and Leleakuhonua in this exclusive and deeply mysterious club. Sednoids are the objects that originally inspired the Planet 9 hypothesis. They orbit the Sun on enormously elongated paths, with perihelion distances so large that they never come close enough to Neptune for the ice giant to have any influence on their orbits. They are gravitationally detached from the known solar system. Something else must have placed them on these orbits, and something else must be maintaining them. The three previously known sednoids all had their orbits aligned in a similar direction, with their longitudes of perihelion clustered between roughly 0 and 90 degrees. This alignment was one of the strongest pieces of evidence for a massive perturber herding them into formation. But Ammonite broke the pattern. Its longitude of perihelion was measured at approximately 271 degrees, almost exactly opposite to the other three sednoids. It was not aligned with its siblings, it was anti-aligned. Its orbit pointed in the wrong direction. For the Planet 9 hypothesis, this was deeply uncomfortable. If a single massive planet were shepherding all sednoids into a common orbital configuration, why was the newest member of the family facing the other way? The discovery team, led by Yingtung Chen, was cautious, but direct in their assessment. Yukun Huang, who conducted dynamical simulations of Ammonite's orbit at the National Astronomical Observatory of Japan, stated plainly that the misalignment lowered the likelihood of the Planet 9 hypothesis. The simulations showed that if Planet 9 exists, its orbit would need to be significantly farther from the Sun than most current models predicted, pushed out to roughly 500 astronomical units or more, in order to keep Ammonite's orbit stable for at least 1 billion years. That is a substantial shift from the 2025 best fit semi-major axis of 290 astronomical units. The closer models, the ones that best explain the clustering of the other ETNOs and the Neptune crossing objects, could not easily accommodate Ammonite. The planet would need to be farther away, which would weaken its gravitational influence on the inner ETNOs and undermine some of the very evidence that supported the hypothesis in the first place. The team proposed an alternative explanation. Their simulations suggested that all four sednoids may have shared a common orbital alignment roughly 4.2 billion years ago, about 300 million years after the formation of the solar system. Over the subsequent billions of years, the orbits would have slowly drifted apart due to differences in their apsidal precession rates. The gradual rotation of the long axis of each orbit, caused by the combined gravitational influence of the known giant planets. In this scenario, no Planet 9 is needed. The current spread of sednoid orbits is simply the result of a primordial alignment that has been slowly dissolving over geological time. The original alignment might have been caused by a passing rogue star or planet that swept through the outer solar system during its infancy, scattering the icy bodies onto their extreme orbits and then departing forever. Simulations without Planet 9 showed a 97% probability that Ammonite's orbit was previously aligned with the other sednoids 4.2 billion years ago. The gravitational ghost of a long-vanished interloper, not a hidden planet orbiting today, could explain everything. This is a powerful counter-narrative. It takes the same data that supports Planet 9 and reinterprets it through a completely different lens. Instead of a shepherd still guiding the flock, it proposes a shepherd that passed through once, rearranged the landscape, and disappeared. Instead of a planet hiding in the present, it invokes a planet that existed in the past and was ejected. The orbital scars remain, but the object that caused them is long gone. It is worth noting that the Ammonite discovery does not definitively disprove Planet 9. Battigan and Brown's models have always predicted that some fraction of distant objects should occupy anti-aligned orbits relative to the majority. The existence of one anti-aligned sednoid is not inherently fatal to the hypothesis. But with only 4 sednoids known in total, and one of them pointing in the opposite direction, the statistical weight of the alignment argument is weakened. The pattern is less clean than it used to be. The picture is muddier. And in a debate that hinges on small number statistics, every new data point carries disproportionate importance. Beyond observational bias, collective gravity, and ammonite, there are even more exotic alternatives lurking in the margins of the debate. One proposal that has generated significant attention is the idea that the orbital anomalies attributed to Planet 9 might actually be evidence that our understanding of gravity itself is incomplete. In October of 2023, a pair of theoretical physicists published a paper arguing that the same observations motivating the Planet 9 hunt could instead reflect a modification to the law of gravity at extreme distances. In the standard Newtonian framework, gravity falls off with the square of the distance and operates the same way whether you are measuring the pull between two billiard balls or two galaxies. But some physicists have long suspected that Newtonian gravity might break down at very large scales or very low accelerations. The most famous such proposal is modified Newtonian dynamics, or MOND, originally developed to explain the rotation curves of galaxies without invoking dark matter. If something similar operates in the outer solar system, the clustering of ETNO orbits might not require a hidden mass at all. It might simply be the signature of gravity behaving differently than we expect at hundreds of astronomical units. This idea remains highly speculative. MOND and its relatives have a checkered track record. They can explain some observations beautifully while failing spectacularly on others. And the specific proposal linking modified gravity to the Planet 9 observations has not yet been developed into a detailed, testable model that can be compared head-to-head with the planetary hypothesis. But it is a reminder that when the data is limited and the phenomena are at the edge of our observational capabilities, the space of possible explanations is wider than we often assume. There is also the primordial black hole hypothesis, which attracted considerable public attention when it was proposed by physicists Jakob Schultz and James Unwin in 2019. They suggested that the gravitational signatures attributed to Planet 9 might be caused not by a planet but by a small black hole, roughly the mass of 5 to 10 Earths, captured by the solar system in its early history. Primordial black holes are hypothetical objects that may have formed in the extreme conditions of the very early universe, in the first fraction of a second after the Big Bang. Unlike stellar black holes, which form from the collapse of massive stars and have masses of several solar masses or more, primordial black holes could be much smaller. A 5 Earth mass primordial black hole would be roughly the size of a grapefruit. It would be utterly invisible to optical and infrared telescopes because it emits essentially no light. It would interact with the rest of the solar system purely through gravity, producing the same orbital effects as a planet of the same mass. The black hole hypothesis is elegant in the sense that it neatly explains why we cannot find Planet 9 with telescopes. You cannot photograph a grapefruit-sized black hole at 290 astronomical units. No amount of infrared data mining will reveal it. The only way to detect it would be through gravitational lensing effects, the bending of light from background stars as they pass near the black hole, or through the annihilation flares that might occur if the black hole accretes dark matter particles. Both of these detection methods are extraordinarily difficult and would require dedicated campaigns with specialized instruments. The hypothesis remains unconfirmed and is considered unlikely by most astronomers, but it has not been ruled out. It occupies a strange and fascinating corner of the possibility space, a reminder that the unseen object shaping the outer solar system, if it exists, might not be what anyone expects. And then there is the simplest and most deflating possibility of all. What if there is nothing out there? What if the orbital patterns are coincidences, amplified by small number statistics and reinforced by confirmation bias? What if the ETNOs are on their current orbits not because of any hidden perturber, but because of some combination of the known dynamics of the early solar system? Random scattering events during planetary migration and the natural dispersion of orbits over billions of years? This is the null hypothesis, the default position that requires no new objects and no new physics. It is not glamorous. It does not generate headlines, but it is a legitimate scientific position, and it is the position that the evidence must ultimately be measured against. Astronomer David Tholen of the University of Hawaii has described himself as being in the grey area on Planet 9. He has noted that different researchers use different sets of ETNOs to measure clustering, and that the cutoff for which objects are included is somewhat arbitrary. Change the cutoff, and you can get different results. Matthew Holman, a Smithsonian astrophysicist and lecturer at Harvard, has expressed similar uncertainty, stating that he is not sure whether the evidence currently leans one way or another. These are not fringe voices. They are respected experts in orbital dynamics who have looked at the data and concluded that the case is not yet strong enough to pick a side. Catherine Volk, an orbital dynamics researcher at the University of Arizona, initially explored the possibility that a Mars-mass planet might exist within the Kuiper belt itself, much closer than the predicted Planet 9. Additional data eventually undercut her specific proposal, and she has since expressed skepticism about both her own original hypothesis and the standard Planet 9 model. Her current assessment is blunt. She suspects that none of the existing predictions are correct. If there is something out there, it may be fundamentally different from what anyone has imagined. The landscape of competing explanations can feel overwhelming, but what is most striking is that none of the alternatives, taken individually, can do what the Planet 9 hypothesis does. Each one addresses a piece of the puzzle while leaving other pieces unexplained. Observational bias can account for the clustering but struggles with the perpendicular orbits and the solar tilt. Collective gravity demands a reservoir of unseen mass that nobody has found. The primordial alignment story works for the sednoids, but says nothing about the 5 sigma Neptune crossing result from 2024. Modified gravity remains too embryonic to test. And the null hypothesis grows more strained with every new independent line of evidence that converges on the same invisible point. No single alternative matches the explanatory reach of Planet 9, but no single piece of evidence is strong enough to silence the alternatives either. This is the scientific process at its most honest and most uncomfortable. There is no clean answer. There is no moment where the courtroom falls silent and the judge delivers a verdict. There are only competing models, each with strengths and weaknesses, each making predictions that can be tested with future data. The Planet 9 hypothesis is the most comprehensive single explanation currently on the table, but it is not proven. And its competitors, while individually incomplete, collectively demonstrate that the space of possible explanations is far broader than any single narrative would suggest. What we are witnessing is not the triumph of one theory over another. It is the slow, grinding, often frustrating process by which science approaches truth in the presence of limited data. The outer solar system is the most poorly observed region of our cosmic neighborhood. We have discovered fewer than 100 objects in the extreme trans-Neptunian population. Our surveys cover a fraction of the sky to a fraction of the depth needed to be comprehensive. Our dynamical models are sophisticated but built on sparse input data. We are arguing about the architecture of a building we have only seen through a keyhole, and the debate will not be resolved until someone opens the door. That door is now being nudged open by new instruments and new discoveries. But what lies behind it may not be what either side of the debate expects. The solar system has a long history of surprising us, of containing things we never predicted, and lacking things we were certain must exist. Whatever the truth turns out to be, whether it is a hidden planet, a swarm of invisible debris, a fossilized scar from a long-departed interloper, or something we have not yet imagined, the answer will reshape our understanding of how planetary systems form, evolve, and organize themselves across billions of years. And that answer, when it finally arrives, will have been earned not by a single dramatic discovery, but by the slow, patient accumulation of evidence at the very edge of what human instruments can detect.